Hello again. In this lecture, we will solve an example on multistage amplifiers. Uh, you know that we have seen single transistor amplifiers before, but most of the time, one stage amplifier is not good enough to achieve all the specs. Sometimes you need much higher gain, you need to provide like low output impedance or high input impedance, all these conditions at the same amplifier. And to be able to do that, you may need to use multi-stage amplifiers. In fact, the analysis is quite the same. The only difference is as the number of transistors increases, dealing with them, drawing the small signal model and the other things are getting a bit more complicated. So you have to come up with some quick ways or smart ways for analysis. So in this example, we will learn or we will see some examples on that. So in this schematic, we see a multi-stage amplifier. And as you see, we have 3 transistors. So we have 3 stages in here. So when you take a look at the stages, of course, this is our source. This is the first stage. This is the second stage. And we have the last stage amplifier, and we have the load in here. So when we take a look at the first stage, we have a MOSFET. It is depletion type, but I told you before that, either you have enhancement or depletion, that doesn't matter. Small signal analysis does not change at all. It only affects the DC analysis. So when you take a look at this amplifier, this is gate, drain, and source. And source is AC grounded. Therefore, this is common source amplifier. And it has a gain of AV1, let's say. We need to find that AV1. Naming this node as Vx. So we will find the gain AV1, which is Vx divided by V signal. So we can define AV1 as Vx divided by V signal. I will show you in the next slide, but you can imagine that when you're finding this Vx, this second stage introduces some loading, and the loading is the resistance seen in this direction, which is the input resistance of the second stage. So this second stage appears like a simple load resistance in here, where this load resistance value is the input resistance of the second stage. So you can find Vx over V signal in this way. So this is the first stage. The second stage, we have a bipolar transistor, collector, base, and emitter. Again, emitter is AC grounded. Therefore, this amplifier is a common emitter amplifier. We can name this node as Vy. So AV2 is defined as Vy over Vx. Again, when finding Vy, the third stage is simply a resistive load for the first stage. So you need to find the input resistance of the third stage and put it in here like a load resistance to find the gain of the second stage. So the loading coming from the next stage is a pure resistance, which is the input resistance. The third stage, again a bipolar transistor, collector, base, emitter. Collector is AC grounded, so this is common collector amplifier. AV3 is defined as V out divided by Vy, and since it is common collector amplifier, you expect a gain which is less than 1, but for a good design you expect it to be as close as possible to 1. So we have identified the individual stages in this multi-stage amplifier, and because of this findings, this first stage has a high gain, the second stage is common emitter, so it has a high gain. So, the gain from here to here is a very high gain. So you multiply two high gains, you cascade two high gain amplifiers next to each other. So from here to here, you expect a very high gain. The last stage does not introduce a significant gain, but the thing is, your load resistance is a low resistance. You have a load of low resistance. So what you do in here, the resistance seen from here, the output resistance of the common collector amplifier is low, so you provide impedance matching. And I have mentioned about this thing in the very early lectures with the audio amplifier example. At that time I was saying that you were trying to drive a speaker, so you need to use a buffer at the output stage. So it's exactly the same thing. You have a low resistance load. You are using a voltage buffer, which does not introduce a significant gain, but it only matches this load resistance with the low output resistance. And it has high input resistance, which provides matching between this node and this node. So it only provides resistive voltage. It only provides impedance matching between common emitter amplifier and the low load resistance. The first thing that you should do, of course, the DC analysis. The very first thing that you should do is DC analysis. And why do we do the DC analysis? We have two reasons. First, we want to show that, or we want to check the operation regions of transistors. So what we want is MOSFET transistor to be in saturation, bipolar transistors to be in forward active region, so that we can continue with the small signal analysis. If this condition is not satisfied, then we cannot analyze this circuit. We cannot continue with small signal analysis. So the second thing that you should do is, of course, finding the small signal parameters. And we have one advantage in here, that is, these individual stages are not DC coupled. They are DC-wise isolated. Why? Because this C1, this capacitance, and this capacitance isolates the DC operating point of each individual gain stage. So the DC operating point of each stage is independent from each other. So finding the DC operating point is very, very easy. Unfortunately, this may not be the case all the time. As you may have seen in your take-home exam 1, we gave you a two-stage amplifier for DC biasing solution. In that case, there were no isolation capacitances and two stages were affecting each other. In that case, of course, DC analysis is a bit more complicated. But in this particular example, because of this isolation capacitance, finding the DC operating point for each stage is quite easy. So this amplifier is not DC coupled, or stages are DC isolated, or not DC coupled, or not direct coupled. Okay. The first thing that we should do is, of course, DC analysis. I'm sure that you can do it by yourself, using these individual values and setting VDD is equal to 15 volts. Please solve the DC operating points for each transistor as an example, as an exercise. And when you do that, you should find these results. So for the first stage, first transistor, small signal parameters are given by these values. For the second transistor, you should find similar values to this one. And for the last one, you should find these values. So please verify the results as an exercise. This is very straightforward and it can be a good example. And all the values are given in here, by the way, transistor parameters, and you should come up with these results. The next thing that you should do is, of course, small signal analysis. And what we have learned in the previous single transistor amplifiers is that you short the capacitors, kill DC sources, and replace the transistors with their small signal equivalent circuit. But when you take a look at this circuit, we have 3 transistors. Drawing the small signal model takes a lot of time, and you may not even fit it on a simple A4 page. So we have to come up with some smart ways to analyze this whole circuit. As I said, what you can do is you can take a look at the solution stage by stage, where you take into account the loading of the next stage for the first one. So with this knowledge, let's start with the first stage. So you can represent the first stage by this equivalent circuit, where this Rin2 is the loading coming from second stage. So the input resistance of the second stage behaves like RL for the first stage. Okay. So when you find Rin2, you can minimize or simplify the circuit like this thing. Then what I need to do is I need to find again 3 important parameters. One of them is, of course, the input resistance of the first stage, which is in fact Rin of the overall circuit. We need to find R out, and we need to find AV, which is defined as Vx divided by V signal. So I am seeking for these 3 important parameters. What you can do is, of course, you can draw the small signal model. So you can use hybrid pi model, and you can draw the equivalent circuit like this, which is okay. And don't forget to name the nodes. This is Rin2, R signal, and V signal. So Rin is quite obvious in here, I guess. Rin of the overall circuit, or Rin1 is Rg. R out is quite obvious again. R out 1 is R01. How do you find it? When finding the output resistance, kill independent sources, which means that Vg is grounded, Vs is grounded. VGS1 is equal to 0, so this is like an open circuit. And the resistance that you see from here will be R01. And of course, when you write the gain, AV1, let's name it as AV1, which is Vx over V signal, it is a typical common source amplifier gain, which is Rin1 divided by Rin1 plus R signal times GM1 R01 RD and Rin2. So the only unknown in here is Rin2, and we are going to find it on the next slide. when we are dealing with the second stage, but the other parameters are all known. You know about Rin1, which is Rg. We know R signal. Gm1 is known. We find it in the previous slide. Ro1 is known. Rd is known. If you find Rin2 in the next slide, then the first stage gain is okay. You find the first stage gain. You should be able to find these values without even drawing the small signal model. Why? Because when you are taking a look at from here, you see infinite impedance at the gate of the transistor. Therefore, you should be able to say Rin1 is equal to Rg directly. Similarly, since source is grounded, the resistance seen from here has two components, Rd in parallel with Ro1. So you should be able to write Ro1 directly. By the way, I made a mistake in here, so let's correct it. When finding sorry, I'm gonna correct it right now. So here is Rd, Ro1. This is, let's say, Rin2, Rin2. So the output resistance is, in fact, Ro1 in parallel with Rd. Sorry for the mistake, because I draw Rd and Rin1, Rin2 as in parallel as a single resistor. That was a mistake, so I have to put them separately so that Rout has Rd component as well. So this is the corrected version, so please use it. But whatever it is, so when you take a look at this circuit, this schematic again, when you're looking from here, Rout has two components. One of them is Rd, the other one is Ro1. So you should be able to say Rout is equal to Rd in parallel with Ro1 without even drawing the small signal model. For the gain, the same thing again. So you can find Vg potential because gate current of M1 is 0. So Vg is equal to Rin divided by Rin plus R signal times V signal. Source is grounded, so VGS is equal to Vg. So now you can tell this current Gm VGS in terms of V signal. When you multiply this current with the total AC resistance at this node, you can find the output voltage, and the AC resistance at this node has three components, Rin2, Rd in parallel with Ro1. So again, you end up with this AV1 result when you even do not draw the small signal model. So let's take a look at the second stage. So for the first stage, let's repeat the outcomes. Rin1, Rin of the overall circuit, Rg, Rout 1, Rd in parallel with Rout 1, AV1, Vx divided by V signal is minus Rin divided by Rin plus R signal times Gm1 times Rho Rd Rin2. And if I can find this Rin2, then I know AV1 value without any problem. So you can find the numerical values. I'm not going to solve the numerical values. Expressions are more important here. And keep in mind that we never memorize any of these expressions because depending on the circuit type, expressions may change. So try to understand the derivation of these expressions rather than memorizing them. For the second stage, now I'm going to take my input as Vx, which is the output of the first stage. Output of the first stage is taken as the source applied at the second stage. Please note that I don't have a source resistance in here. You don't need to use it. Sometimes your friends or some of the students may confuse it. They can think that the output resistance that you see in here should be included as the source resistance, source internal resistance, but it is not correct because Vx directly appears at this node, and it does not have any voltage drop across Rout1. So Rout1 appears like a parallel resistance in here. So you don't need to take into account. It's already given in this voltage. This voltage already includes the effect of Rout1. So you never use a source resistance in here. Again, we are looking for three important parameters: Rin, 2, which is critical for the first stage gain, of course, Rout2, and of course AV2 defined as Vy divided by Vx. And please note that this Rin2 is the loading effect of third stage. Again, we can draw the small signal model for solving these gain and input-output resistances, but I'm sure that you can see them directly. We are looking from here, we are trying to find Rin2. What we have is, of course, R1 in parallel with R2, in parallel with the resistance seen from here. And the resistance seen from here is quite easy because emitter is AC grounded, so you have R pi 2 resistance. So Rin2 should be equal to R1 in parallel with R2 in parallel with R pi 2. For the output resistance, you are looking from here. We have two components, Rd in parallel with the resistance seen in this direction, which is Rout2, because it's a common emitter amplifier. So Rout2 should be written as RO2 in parallel with Rd again. And for the gain, this Vx appears directly at the base of Q2. Base emitter voltage is directly equal to Vx. So we have GmVx current passing through here. If you multiply this GmVx with the AC resistance at this node, you will find Vy, which is minus Gm2 times Rin3 in parallel with Rd in parallel with RO2. Let's verify this thing by drawing the small signal model. You see that we got the same result anyway. So the small signal model is this: Vx R1 in parallel with R2. We hit the base right now. R pi 2. Emitter is grounded. RO2. GM2 V pi 2. Collector RD and Rin2. Rin3, sorry. Of course, Rin is this resistance, Rin2. And as you see, my initial guess was correct. This thing is equal to R1 in parallel with R2 in parallel with R pi 2. The resistance seen from here you kill the independent sources. This is shorted. VBE or V pi 2 is 0. This is open. The output resistance that you see is RO2 is equal to RO2 in parallel with RD, which is again consistent with what I was guessing before. And the last thing is the gain. Vy is this voltage. This Gm V pi 2 is passing through these three parallel resistances, and V pi 2 is directly equal to Vx. So AV2 can be written as minus GM2 RO2 RD. Let's say this is RD2, not to confuse with the first stage. RD, Rin 3. So we find the second stage gain as well. The only thing that we don't know in here is this Rin 3, and we will find it in the next slide when we come to the calculation of input resistance of the third stage. So as you see, you don't need to draw the small signal model each time. You can find R in R out easily, especially for common emitter and common source amplifiers. If you don't have degeneration, things are quite straightforward. So you should be able to calculate them. And for the last stage, now the output of the second stage is the input. Again, we don't have any resistance in here. It's just like shorted. And this is a common collector amplifier I told you before. Input resistance are in 3, which we will use for the gain of the second stage. R out 3, which is in fact R out of overall circuit. And the gain is AV3 is defined as V out divided by V by. So when you take a look at this circuit, you should be able to see R in 3 directly, I guess, again, because it's like R3 in parallel with R4. The resistance seen from here. You have now resistance at the emitter. This makes the things complicated by using reflection rule. You just multiply it by beta plus 1, and you should add R pi of Q3. So you can say that input resistance is R3 in parallel with R4 in parallel with R pi 3 plus beta plus 1, R5 in parallel with R6. So let's draw the small signal model to prove this. Again, we apply Vy at the input. We have R1 in parallel with R2, base, collector is grounded, Gm V pi 3 plus minus V pi 3, emitter, at the emitter I have R5 and R6, of course, sorry, RL. R0 is in here, but since one end is grounded, I'm not gonna put it there, I'm gonna put it in here. It's not gonna change any result because one end is already grounded, so I can erase that R out over there and I can put it in here. And when you are looking for the input resistance, R in, we have R1 in parallel with R2, sorry, this is R3 and R4, let's correct it. We have R3 in parallel with R4, and then we have the base resistance R pi 3, and we have to reflect this thing up in there by multiplying it by beta plus 1. Why? Because the current passing through here is I base. The current passing through here is beta plus 1 I base. By using reflection, you can transfer all these three resistances right in here in series with R pi 3. So R in 3 from this approach can be written as R3, R4. I want to write it in a clear place, so let's write it in here. Oops. R in 3, R3, R4, R pi 3 plus beta plus 1, R5, RL and RO3. So this will be the loading resistor for the second stage. So you're going to use this expression in here to find the second stage gain. The next thing that we should do is the voltage gain. So let's find AV3, which is V out divided by VY, and I'm going to copy this thing from there. So V out is this node. So there is 2 times resistive division. The first is between VB and VY. The second thing is between VB and VE. So the first one can be written as, in fact, like VB is equal to VY. Sorry, we don't need to do that. So VB is equal to VY and VE is equal to, again by using reflection, you can say that it is like beta plus 1 RO3 R5 R6 divided by R pi 3 plus beta plus 1 R5 R6. You have resistive voltage division in here after reflection. So this will be your gain. In fact, this thing is VB. So you can write this term as AV3. This term in here will be the AV3. Okay, so this is the last stage gain then. And the last thing is the output resistance.